So thank you, and thank to the organizers for letting me give this talk. I never given a video talk like that before, but I hope it will work. This talk is a kind of survey talk, so I will. It will be very much about. Goes back quite a long time, actually, to work by Hermander in the 60s on non-self-adjoint operators and non-solvability. And then through my thesis, I came into the subject of Fourier integral operators with complex phase. And this is very much related. It had applications to the Bergman kernels. So I would like to review that a little bit and then come to more recent results in the analytic case. So let me go on. So this was I will speak a little about the earlier works by Pfefferman and then by Boutet-de-Monvel and myself about the singularity of the Bergman kernel in the case of strictly pseudoconvex domains. And then it turned out, then there was a new interest in Bergman kernels through, in the case of high powers of line bundles. And it turned out that the technology of working in exponentially weighted spaces of holomorphic functions was very useful here. Huh? And then, and then I will speak about more recent works on in the real analytic case. Huh? So let me go on with first review some old work where you start with complex phase operators, and this really comes from has its origins in the work of, in the famous counterexample of Hans Levy for solvabilities, for non-locals, for local solvability. And then the work by Hermander in 1960, as I mentioned. So then in my thesis, and then in a later work with, slightly later with Duistermaat, we considered a class of pseudo-differential operators with principal symbol P. Unfortunately, I don't have a hand. I don't know how to point. Maybe if I can. So I take and I assume that the Poisson bracket is non-vanishing on the characteristics. Huh? And then you then you look at the subset of characteristic points where the Poisson bracket is positive or negative. And then in my thesis, and then in the form I present now in a joint work with Duistermaat, we show that you can find operators F, F plus, and F minus acting on distributions on my compact manifold, which are pseudo-local, and F plus is concentrated near sigma plus, and F minus is concentrated near sigma minus. And they have this property here. Huh? And from this, you can actually deduce that if you take, if you compose, now let's say you take one of the equations here, and you, I have P acting to the left in the first equation here. Let P act to the left, then you can show that actually P will annihilate F plus to up to smooth operators. So therefore, what we have found here are in a way the microlocal orthogonal projections onto the kernel of P and the co-kernel and the kernel of the adjoint. Huh? And then with Anders Melin, we developed a complex phase version of the Hermander's theory of Fourier integral operators, which was somewhat parallel with, there were parallel evolution developments by Maslov and Kucherenko and other people in the Russian school. So applying that theory, we checked that these operators F plus and F minus are actually globally well-defined Fourier integral operators associated to a complex canonical relation. Now let's see here. And from that, it was very natural to go on. Then there was the work by Pfefferman, which I mentioned before, and some work by Boutet-de-Monvel about the Bergman kernel and about systems of pseudo-differential operators. So it was very natural to try to adapt, to apply Fourier integral operators with complex phase to this situation. So let's take a domain with smooth boundary. And then on this domain, we can define the Bergman projection. It's the orthogonal projection from L2 to the subspace of holomorphic functions in L2. And then for this, then there is the corresponding space of solutions to the D bar B equation, and there is a corresponding projection called the Seger projection. It's this one. And then it turned out that this is extremely close to the situation we studied with Deuster-Matt. Huh? And so the Seger projection corresponds very much to the operator F plus. And from that, we could apply with Boutet-de-Monvel the global theory of Fourier integral operators with complex phase, and the result is as follows. Huh? So let us define what happens now. Let us define our domain by an inequality phi is negative, where phi is smooth with non-vanishing differential on the boundary. And then we take the polarization of phi, which is the function which in the double number of variables, which is equal to phi on the anti-diagonal. So when y is equal to x bar, it should was given by phi of x. And this function, as far as I know, was introduced by Hermander in an unpublished paper where he tried to get the asymptotics for the Bergman kernel. So the condition in the smooth situation is that this extension should satisfy the D-bar equations to infinite order on the anti-diagonal. And then with Boutet-de-Monvel, we showed that the Seger projector is a Fourier integral operator with complex phase. And we could, using this function psi, we could give a fairly explicit representation. So here is our Fourier integral operator with a globally defined phase function. And the fiber variables go from 0, or is the variable t on R plus. And correspondingly, there is a classical symbol given a fairly explicit. Sorry, there was a question, I think, but
maybe it was just some noise on the line.
Okay. So, the corresponding, there is a classical symbol which has an asymptotic expansion in homogeneous terms in the fiber variables, but there is only one fiber variable, so it takes, oh sorry, there should not be any t here. I don't know how to erase it. Oh, no, it doesn't work anymore. Oh, I know why. I have to go back, sorry. Because I colored something else. No, sorry. I used to be able to No, never, never. So there was a similar result for the Bergman kernel. And the only difference is that the symbol is one degree of higher order. So it starts by t to the power n, and here it's by t to the power n minus 1. So that was, I think, quite. There was some difficulties to overcome. We worked with reductions to the boundary and so on. Let me go to. So then, more recently, I was interested in high powers of a complex line bundle. So this was started by work by Dijon in 1990, and then there was work by Catlin and Zeldich. So let me explain the situation. I take a complex line bundle on a complex compact manifold X, and I assume that this line bundle is equipped with a metric. It means that over each point I have a norm on my on the elements of my line bundle. And this norm, it's not written here, it's supposed to depend smoothly on the base variable. Then we can define a curvature form. I take a section, I take a holomorphic section, which locally is non-vanishing. Then I can write the corresponding norm on the form e to the power 5 for some smooth real valued function phi. And the curvature form is this 1, 1 form. And you can check directly, for instance, if you change the section here, then this quantity remains unchanged, because to change the section means that you add the pluriharmonic term to phi. So this Levy form is unchanged. Now go from L to a high power of the line bundles. It means that, let me see. So the local section of my line bundle is of the form U times S, where S is this special non-vanishing section, and U is a scalar holomorphic function. And local sections of this high power are just of the form U times S to the power K. So the norm of S to the power K will be E to the power K phi. Now I can recover the painting possibility. So therefore, a general section of L to the power K locally is of this form, where U is holomorphic. And this means that my problem, at least locally, to study high powers of line bundles and sections in such a bundle, is to study holomorphic functions which belong to the L2 space with this exponential weight. So L dx is the well, here we can take the Lebesgue measure or some other invariantly defined measure related to the geometry. And then I have the exponential weight sitting here. So this space, I will call it L2 phi omega. And this, I will call it H phi omega. And such spaces, I worked a lot with such spaces when I worked in analytic microlocal analysis. They come up very naturally in connection with FBI transforms. So here, this was a good surprise for me because it's the same situation comes directly in the context of Bergman projections for powers of line bundles. So, and then the theorem of Catlin and Zeldich was that locally the Bergman projection for high powers of a line bundle L with non-vanishing curvature, takes this form, which is, it looks very much as the one you had for the Bergman and the Seeger kernels. we have the polarization of phi. We have a classical symbol here of order n. And these functions are holomorphic to infinite order on the anti-diagonal. So this is the local statement. And another feature here is that there is a classical inequality for if you compare polarizations with the weights, it's namely this inequality here. And this inequality means that if I reduce my operator, so this operator pi of k acts on the space L2 phi, a high power of, maybe I believe I have this on the next slide. So this implies, this inequality shows directly that this operator pi of k has a nice L2 boundedness in my weighted L2 space. And the proof of Catlin and Zeldich was to use my old result with Boutet-Monvel. So let me go to the next. So then with Bergman and Bergman, we came up with a direct proof. It was very natural because it's so close to things that I were used to do. So I worked in an H phi space. I forgot if so H phi means these are the spaces of functions which are in L2 with a growth like e to the power phi over h. And when you go from global to local theory, then you can replace the large parameter k with a small semi-classical parameter h by this this relation here. And then for such operators, pseudo-differential operators are very simple to handle, and they are given by this formula 2 here. So this is just a standard formula for a semi-classical pseudo-differential operator. The only difference is that we are now in a weighted space of holomorphic functions, so we cannot. So we have to specify a contour of integration. And the contour of integration is this thing here. I cannot, maybe I can paint it with this one here. And then you show that if b is equal to 1, we have the identity operator up to small errors. And to get the Bergman kernel for the weighted H phi space, what you do is that we try to well, actually, what you can do is that we know what the operator should look like. It should look like this, and then you go backwards and you say, if I use my polarization, I consider y bar as an independent variable theta, then phi of y should become the function psi of y and y bar, and I should have an so my identity operator should. I would like to try to write my identity operator as this. And then if I have convenient enough holomorphy in X and anti-holomorphy in Y, it's actually enough to find the identity operator in this form, and then I will get approximately the Bergman projection. So how do you go from an operator of the type 2 to an operator of type 3? Well, in the talk of Gerd Grove, there was the Kuranishi trick. So we also used the Kuranishi trick to show that the two representations are equivalent. So I start with the second representation, and I have this thing in the face, and by Taylor expansion, I write it as x minus y dot a vector. So we are now in holomorphic or almost holomorphic category. So This is just the standard bilinear product on CM. Huh? I take the sum of the coordinates of this times the coordinates of this. Huh? So this is so by a change of variables, I just now replace theta by eta. Huh? However, there was still a problem. So let's go back. This gives me an operator of the form 3, which is then if I take theta equal to y bar, I have the equation 4. I forgot to mention that there is a thing missing here, namely I want only dependence on x and y bar. I don't want this dependence here. So I need to eliminate the y variable. Huh? So, but this again, into the differential theory, it's rather standard to do. What is the most important is the restriction to the diagonal when y is equal to x. And then you can do divisions and other tricks to get to eliminate. You can do successive eliminations of the second variable y. So it's this variable here which should be eliminated. And this way we were able to give a fairly short direct proof of the results of Catlin and Zeldich. So we did not have to pass using the old work with Boutet-Monvel. Now, more recently, there has been interest in the case of analytic line bundle. So of course, it's already a holomorphic line bundle. But so analytic means that the metric should be a real analytic function of the base variable. And then, so if I rephrase the result, I can rephrase the result of Catlin and Zeldich by saying that my Bergman projection is of this form, where I have a general distribution kernel, which is holomorphic and anti-holomorphic in x and y. I cannot. And with Michael Hittrick, we and maybe Coburn, we reviewed some of the Schwarz. So this is a version of the Schwarz kernel theorem in the holomorphic setting, that you have such a distribution sitting here, which is partially holomorphic and anti-holomorphic. So if I reduce this operator to an operator going from instead of going from the weighted L2 spaces but ordinary L2 spaces, I should do this conjugation. Then I should conjugate my kernel by these two factors, by this one and this one. And if I do that, then the results of Catlin and Zeldich says that the difference is O of H infinity. So in the analytic case, what was expected is that this will work with an analytic symbol in the sense of Boutet-Monvel and Cré. And instead of O infinity here, we should have something exponentially small. So I think I have only 5 minutes left. So let me. So this slide shows reviews quickly the definition of classical analytic symbols. It's just an ordinary symbol, but with a growth condition here, given in the equation 6. And if you have a formal classical analytic symbol in this sense, then you can have a realization where you stop the summation at a level where the general term in your sum is exponentially small. And then the recent result was obtained by Ruby and Vuengok and myself, and independently by Alix Delporte it says that if my line bundle has a real analytic metric, then in the formula, in this formula here, then I have this relation here. Then psi will be a holomorphic and anti-holomorphic function, and this is valid with an exponentially small error instead of just rapid decay. Okay, and so how did we prove this? Well, we followed somehow the ideas that with Bergman, Dijon and Bergman. And we reduce, so we look for, so we write the operator we want, and we reduce it to a pseudo-differential operator. Then there were many, to do this in the framework of analytic functions, called some technical problems, because there are repeated divisions and other manipulations, and it's difficult to follow with, to show that in the end you go both ways and get analytic symbols. But we can go the direct way to an operator of the form 1. Let me see here. 1, yeah, so if I have an operator of this form, then I can go to a pseudo-differential of this form. And the difficulty is to go in the other direction. And then the observation, which again has been used in other works, is to say that this to go from the formula 1 to this formula 7 is actually a Fourier integral operator acting on the symbol A we had in formula 1. And this is an elliptic analytic Fourier integral operator. All the various steps in the construction do that. And you can compute the canonical transformation of this Fourier integral operator, and it maps the 0 section to the 0 section. And then thanks to a remark, which an old remark, this implies that if it's also an elliptic operator. In this case, it introduces a bijection in the space of classical analytic symbols. The proof of Delporte uses more hard work with analytic symbols. And there have been other proofs by Laurent Charles, and Hezari and Xu, slightly more recent. So then a final remark, we did a final observation in other problems. If phi is slightly degenerate, the Kuranishi trick poses some problems. So therefore one would like to finally get rid of the Kuranishi trick in some situations. And you do that by the following observation. We look for our projection on this form. And we want, instead of trying to prove directly the reproducing property, we write it in a weak form, the reproducing property. Namely, we require that the scalar product with the second HV function should be equal to this scalar product here. So we want to check this. Huh? And then you just plug this into the equation. So and this gives the reproducing property with a small error. Huh? So how do we do? Well, the scalar product, I polarize everything. I have this identity here. Then I do the same thing with the scalar product of pi u and v. Huh? Then I get many integrals. So here I have pi. The interior integral here is, sorry, I cannot. So this double integral sitting inside, that's the pi u, and then the scalar product with v. And here I use formally the Fubini Theorem. And I see that I get my weak identity if I can solve the equation 9. If I can find an analytic symbol A so that this holds, then I'm done. Huh? And this I can rewrite in the form 10. So again, this is now a more explicit Fourier integral operator acting on my unknown real analytic symbol A, and I want to choose A, so I get 1. But again, my Fourier integral operator is associated to canonical transformation, which maps the 0 section to the 0 section. So therefore, I know that I can solve this. And we hope to use this in other work with Michael Hittrick. We need this alternative point of view on the Bergman kernel. So I thank you for your attention.
Yes, thank you very much. Thank you very much. So, are there any questions, remarks?
If I may, I'd like to
Yes.
ask a question. So, Johannes, do you think you can extend such a theory in the case of some magnetic operators?
It's extremely close to the now what is it called? It's not it's called the Pauli operator, I think, the magnetic Schrödinger operator in yes, if I have a magnetic Schrödinger operator in 2 dimensions, I think it's oh yes, it's there. Then in that case I'm on an unbounded, usually I'm on Rn. And then I have a whole bunch of exponentially small eigenvalues. So I have the telephone ringing here, but I will let it go on ringing. So yes, the answer is yes. Everything is possible, but I don't know if it has been done like that yet.
And do you think also you can apply this to have some kind of spectral results about the Barr-Neumann problem, since it involves some projectors?
That is then you have a boundary value problem, and you can. There is Xinju Xiao has worked on such questions, but in the analytic case, it's not yet done to my knowledge, and so it's.
And then in the case of Dirac operators.
I'm less familiar with the Dirac operator, but it's quite possible. And actually, there are some very nice spectra problems. When you for the other question, you can what one would like to do is to look at case if I take a line bundle where the curvature changes sign. So it can be positive on one side, and then negative. Suppose I'm in complex dimension 1 already, and I have a change of sign in the curvature, there can be lots of exponentially small eigenvalues which are not 0, and then you can ask what about the projection to the corresponding spectral subspace.
Yes. Thank you.
Thank you. Are there any other questions? So maybe I have a small question. I wouldn't be sure in terms of applications, but of course here you use there are smooth results, but you also use some analytic techniques. But so as I say, I'm not sure about applications. But can you would this go through for Gevrey type of regularity?
I think I haven't looked at that, but I think that Delporte did something in the Gevrey case, yes. And we have some work with Richard Lascar and Meyer Zerzeri. We also look at Gevrey pseudo-differential operators in the framework of H-phi spaces. Huh? And it's not, there are some nice questions which come up. It's not a routine adaptation of, it's not a routine interpolation of C infinity and analytic.
But would it have some practical meaning? I guess so, but for some kind of problems.
If I do Gevrey, huh?
Yeah, yes.
I can, there has been a huge number of works on Gevrey in connection with hyperbolic operators. Huh? I don't know if the practical meaning I don't know, but it's interesting because there is always some critical Gevrey index. So on, if you're on one side, the results look like infinity ones, and on the other sides they look like analytic ones. Huh? And for instance, if you have a hyperbolic operator with multiple characteristics, then lower order terms are important only if I'm on the smooth side, but if I'm very close to analytic spaces, it's known that you don't need any low conditions on the lower order terms. And there is also the very nice result of Lebeau, classical result, saying that if I look at diffraction of singularities, then there is the Gevrey index 3 is how do you say, it's a limiting case. Huh? So for lower than 3, the singularities are diffracted, like in the analytic case, and for over 3, there is a non-diffraction of singularities. Singularities getting to the boundary go straight on. Huh? So it's true that all this, for myself, this was the starting point of all these developments, was to look at such propagation problems in the analytic case.
Yes, because indeed for the systems, if you even for scalar hyperbolic equations, if you have multiplicities or you have low regularity of coefficients, then like Hölder, like we heard in the grad group talks, and Gevrey solutions appear naturally. There is no C infinity well-posedness, but of course you had in your papers with Mellin, you had almost analytic extensions, but that was for the smooth setting. So here somehow you say that the phase function is analytic immediately. So then I wonder if also this your theory with Mellin, if it would have some Gevrey counterpart, if it would help or not.
There is an intermediate, almost Gevrey, almost analytic extensions. Huh? So we did that. So actually, we are working on that. So there was a we saw a very big paper on the archive, not very old, by Fürdeus and collaborators. They have a whole development about they discuss almost holomorphic extensions for Gevrey spaces and many other spaces. And this goes back now. Let's see to. So I think, I mean, I don't know if it has any practical importance, but I think it can keep a lot of people busy.
Yeah, that was my point. That while they appear naturally in solving PDEs, then here it's either just purely mathematical question of curiosity, or it has some specific
Yes, I mean, for me, Bergman, it was nice for me to come back to the Bergman kernel, but there were many other, obviously involved in many other developments, maybe more directly to questions of propagation of singularities before, where I used the same techniques. And there were difficulties with the Gevrey approach. There have been difficulties, but I'm not so familiar with that. So right now, I'm only making we are doing a small job just to see what happens if I use H-phi techniques to Gevrey questions. But I'm not sure that we will solve any difficult problem. We give